start the lecture on nanotechnology and chemical engineering. So we already have studied various nanomaterials, how to prepare various nanomaterials that we have done. So now once we have prepared the nanomaterials, the characterizations of the nanomaterials, so that is very important. So there are various analysis technique or characterizations are available to characterize the nanomaterials or nanoparticles, nanoporous materials, whatever we will synthesize. So today we'll basically discuss a same image analysis ACM. So basic instruments that we'll discuss. You see microscopic techniques, various microscopic technique that we'll discuss. Then same reduction analysis and few examples that we'll discuss on this particular technique. So commonly used analysis techniques that usually used for various material synthesis and analysis. So those are microscopic techniques, SAME, TEM, HTM, AFM. These are the characterizations techniques are used, commonly used, and physical methods of characterizations of the materials whatever we prepare, BT analysis, zeta potentials that usually used. Also diffraction techniques are available, so that is X-ray diffractions, and other techniques are also available to characterize the materials whether it is crystalline, amorphous, and some few spectroscopic techniques are also available, so that is UV NIR spectroscopy, FTR spectroscopy, Raman spectroscopy, XPS, AES. Many are available to characterize the materials whatever that is synthesized, to characterize its particular properties or specific property. Also electric and magnetic property or materials that we can develop or we can synthesize, that also can be characterized by using a specific technique. And mechanical measurements, hardness, strength, that also can be means characterized as that by using a specific techniques. Or some thermal analysis also available like TG analysis, so we can use those techniques to characterize the materials. So why means the materials whatever we synthesize, that may be porous materials, that micropores, mesopores, macropores may be present, or maybe a materials having low surface area, high surface area, crystalline materials, amorphous material, or that materials whatever we synthesize, that may be acidic, basic strength or basic properties present, or maybe thermal stability, redox properties, oxidation state, electronic property, surface morphology, elements present, that also very important. Also vibrational characteristics of that materials, particle size, shapes, many components, or many way we can analyze the materials whatever we have synthesized in the form of nano. So based on that, the specific property means the material possessing, so based on that its performance will change. So this, since nanomaterials we can use or apply various applications, maybe wastewater treatments, reactions engineering, heat transfer, fluid dynamics, many places we can use this nanomaterials. So this nanomaterials performance depends in specific properties. If you are able to increase that specific property, let's say high surface area materials, if you are able to develop. So initially a materials we are using is having, let's say, very low surface area, and by using some techniques, method of preparations, if you are able to enhance the surface area, means some large particles to smaller particles, if you are able to form, then the performance of the materials will be increased, means we can get high conversions, high yield, high selectivity of that specific product. Okay, so this characterization techniques or the specific analysis techniques that would help us. Suppose same using the same materials, if we can prepare 2-3 different type of materials, but component compositions are same, but maybe performance are different, so that actually this analysis techniques will help us to know their physical chemical properties, as well as we can establish a correlations among them, so with that particular material property and its performance. So today we'll just discuss about few analysis techniques, that is microscopic techniques. So the microscopic technique we can classify optical microscope, confocal microscope, and electron microscopes. And under electron microscope, so there is same FECM analysis, EDAX analysis, and STEM image analysis. So these are the things. So we'll start from the optical microscopic analysis, and then confocals, and we'll details discuss about FECM image analysis, basic instruments, and few examples of image, how to analyze them, so that we'll discuss. So to talk about the nanomaterials, so the materials we can prepare in the form of colloids that is present in a solutions, or we can prepare it as powder samples that is in some metal oxides or in metal sulfides, any forms that is in the form of particles, the nanomaterials we can prepare, or we can prepare the nanomaterials from that solutions to thin films we can prepare. So these are the various forms we can prepare the nanomaterials, and then we have to characterize it. So through that characterization, so we can get the size of the materials that we have prepared up to what, once the materials reach nanometer range, so that means what would be the actual diameter, dimensions, length, whatever, if that is in nano range. So that size we can get crystalline size, compositions analysis, thermal state, chemical state, optical and magnetic properties. These are the things very important. So now if you talk about the optical microscope, so in this type of microscope is very old. So yeah, in this particular type of microscope or optical microscopes, it is used lens. Okay, so since the whenever we prepare any sample, so we have to check the samples quality, means the way we have prepared. So if whether there is any presence of crack presents in that particular samples or not, or agglomerations presents in it or not, so that we have to check. So that material property, that is one property. So once we prepare the sample, so once we see, we can see through that our naked eye, so we cannot get it, means particular image, or we cannot characterize property of that material. So since suppose we have a materials having or object that is smaller than 25 nanometer, so I cannot produce a sharp image of that object. So naked eye, it is very difficult to analyze. So since human eye cannot detect object less than 100 micrometers, we cannot distinguish. Suppose two different materials having 100 micrometers that is placed together, so we cannot distinguish them, so it is very difficult for them. So then we have to take help from an instrument, so that is optical microscope. So that will use and to get a specific image of that materials, and then we can identify or we can distinguish that materials. So for that, a set of lenses are used, so to improve the sample illuminations, sample movement stage sometimes is used for this type of optical microscopes, and lens with different magnifications we can use, camera with various apertures or other facilities that can be developed in this type of microscopes to obtain a good quality image of that particular specific object. So here you can see the first one. So here let's say object is here. So suppose you using our human eye, we can see that particular object. So when this object is present here, let's say, and in place of that, if we put some convex lens, so then if that object or materials is further, then clear image we can get. Actually that object that would magnify, so we can get a clear image of that particular species. Okay, so that actually that object whatever that is present, and with the help of that objective lens or lens, that would help to get a clear pictures of that particular image. So when this particular type of means microscopes we are using, so when suppose you have a flat surface, so where the incident ray that would falls, and then so that would reflect to the detectors, means we can say our eye, or if it is humans then eye, and if it is instrument that is detector, so through that the reflected rays that would come to the detector, by that way we can get a specific object image. So when it is rough surface, then the incident lights rays whatever fall on the surface, so that diffracted or scattered light quantity would be very low. So therefore the image would be, the light would come here very less amount of light, so detections would be very not good. So that way if it is when it is rough surface, so instead of flat surface. So that is the nature of the surface of the materials that we prefer, that whether it is flats or rough surface, that depends on the nature of the material. So here our objective is to get a good resolutions or good image of that materials of whatever we have prepared that is present in nanoscale. So therefore so we have to increase the resolutions, we have to use this lens, so then we can get a good magnified or magnifications we can get by using this. So later, so there is a confocal microscope. So here some object lens that would be used, with that some electromagnetic radiations that would be used with that. So in earlier one optical microscope, so there's only lens was used, that is very basic, and then with that lens, if we use some electromagnetic radiations, so then we can get a good image, better image, resolution should be much more better. Okay, so in this case actually objective I said to improve the resolutions of the image or the materials, the structure that materials we have prepared. So to analysis, for analysis purpose it would help. So in this type of confocal microscope, source of light that is present, that is electromagnetic radiations, and we have to use some detectors that is would be present, and light that would from the source, it would be focused on the specimens or the samples, and after that we can get the samples, means particular image we can get by using electromagnetic radiations through that detectors. Okay, so we can get high resolution image with that particular confocal microscopes using. Next is that electron microscope. So in that case, in case of I said optical microscopes, we have to use only a set of lens to get a better resolutions of the object of the materials, and in case of the confocal microscopes, so with the glass or lens electromagnetic radiations we can use to get a better image or resolutions. So after that electron microscope, that is much more better. So in case magnetic lens or electrostatic lens we have to use, with that electrons that would be used instead of electromagnetic radiations or normal lights, instead of that we can use to get a better resolution. So here in this particular electron microscopes, here electrons would be used, that is electromagnetic radiations, and the lens, magnetic lenses we have to use instead of glass lens. In case of optical microscopes or confocal microscopes, so there's we use some glass lenses, but in case of theirs here we have to use some electrostatic or magnetic lenses that we have to use instead of glass lenses. And this type of electron microscopes, so that is two different types, so same and tame. So scanning and transmitting mode, so both way we can means categorize them. So types same and teams these two. So today we will discuss about SEMS or scanning electron microscopes basically. So here in SEM, so the backscattered electrons, so electron guns we have to use that would pass through different lenses, and then that would be fall on the object or the specimens. So then we can get say image of that particular samples of nanomaterial that is present at the bottom. So from that we can get, so in this particular to get image of that surface of the specimens of the materials, so a thick samples is okay, no problem. So since we are using backscattered electrons to get that image, so it is not our problem. So and for that also we have to use some vacuum chamber, so where the materials will be placed, and through that the electron guns that would be passed through this lens and passed and fall over to the material. So the chamber should be vacuum, so otherwise, so due to the presence of shears, so some scattering or other contaminations will come, so we not get good image. And TM, so that is also similar types of, here electrons also would be transmitted through the samples. So in this case, instead of very thick samples we have to use very thin samples. Samples preparation is very important in case of the TM, so that we will discuss much more details later. And in this case also vacuum chambers is required. So these are the basics components, so in to these two microscopic techniques. So now let's say if we talk about the same or scanning electrons microscope, so here let's say we have prepared some porous materials or ceramic metal oxides or metal oxides, iron oxides we have prepared. So it looks like this. So and then if you put in the same, then to get the analysis, so then we can get this type of image. So further magnification, so we can get this type of needles or rod like structures of that material. So these materials actually present this type of means the crystals or structures that materials form. So it would be like this. Okay, so this actually would give us a good structure about that materials. So based on that we can analyze, so which particular means specific means type of structures is helpful for a specific applications. So depending this same actually that was discovered 1986 by some physics, so Nobel means Nobelite. So Iris G. Bennings and H. Rohrer, they were awarded Nobel Prize for this particular technique. So they have first introduced, and This is the instruments actually details. So here's some source would be there, electron source, and that would be condense lens is there. This is the electron guns condense lens, and then that would be passed through the specimens is or samples is here, and after that whatever the transmitted electrons that is coming that fall over the sample, so that would be backscatter electrons, that would be electrons are emitted from the hot filaments, and then some cathodes or that would be means this same, that may be also two different types. So normal seams when a hot filament is used as a source of electrons. So electrons, I said here electrons guns is there. So gradually it has been developed. So means electrons guns that may be hot filaments we can use. So that is conventional same. And so when that electron guns that would be used by using some cold cathodes without any heatings. So electrons that would be emitted from that source, cathode source, so that is remain cold. So then we can efficient. So that is the basic difference in between them. So a cathode that would emit electrons and that would pass through a high electric fields, and by that way means it would fall over the surface of that specimens and to get that image. Okay. So in this particular same episems whatever, so there's we have to use backscatter electrons, or it can be said as secondary electrons. So that would be once it is fall over the samples, that would be scattered and that would be collected in a particular detectors, and we can get a clear image of that particular specimen or samples that would be used as a specimens. Okay. So here with that also means not only image, so with that EDAX analysis also we can do energy dispersive analysis of X-ray, that would be comes from that specimen, so that we can collect the X-rays and that with the help of some detectors. So elemental analysis or composition analysis of that samples means with that suppose a specimen is there made of 2-3 reference elements, maybe coppers, maybe irons. So with the help of ACM image we can get in clear structures or specifics, whether it is spherical shapes or it is cylindrical shapes, different or maybe octahedral shapes of that crystals is present, or that surface of that particular materials is present, that we can say through that image and ACM image we can get. And other than some means EDAX analysis I said, so with the help of EDAX, so elemental compositions, weight percentage of each metals is present in that particular specimen of the samples, that composition analysis that we can get with this help of EDAX. So with the same instruments we can both this elemental analysis, you can say here the image EDAX analysis, so that actually instruments would gives. So with that help, so what are the different elements are present and how much quantity that we can quantify with that help of also that analysis. So here same image of carbon materials, so that we can prepare the nanomaterials. So here today we'll discuss some carbon based nanomaterials or some other nanomaterials also. So once we prepare the nanomaterials, we can get with the help of ACM instruments the image will get. So the property of the materials I said that may be different. So let's say carbons we can make it is graphenes, graphites or CNT at different way fullerenes we can make. So made of carbons but different type of allotropes or structures it's formed. So with the help of means one materials to another, so that we can prepare by considering different factors, means various biomass species, biomass precursors we can use. So get a specific material, so source of biomass or that material source of precursors to get that particular materials. So depending upon the source, the property also would change. So here's metal precursors also we can take metal oxides, metal nitrates, metal sulfates, metal chlorides or metal acetates. Different type of precursors we can take to start or prepare the nanomaterials or that materials will want to prepare. So depending upon the precursors also it would change its property, that will see with the help of ACM image. Various metal oxides phase, different etching times. So we said that nano silicons, porous silicons, if you want to prepare, so then there you have to use some etching materials, so HFs or other things you have to use to develop force inside of that material. So the etching times, if we vary from 10 to 20 30 minutes, so then the property also will change, different type of pores would form. At the same times, heating rate, sometimes you have to heat it up that materials to evaporate the solvent which presents or to change one particular structure to the another structure. So then sometimes we heat up that materials or calcine that materials at low temperature, sometimes at high temperature, and the rate of heating is also sometimes low, sometimes is high. So depending upon that, material property also will change, and effect of synthesis methods is also will affect the material property. Different concentrations of the materials we can take, so that would affect overall properties of that material. So here you can see the graphene was taken, so that is one carbon allotrope, so it is 2D structure. So here's hexagonal structure of carbon carbon bond is there, so this structure. So here if we get in HTM image, so we get gates like this, and ACM image we can get it's like this type of structures. Okay, so here's some others different model carbon materials that was taken. So here you can see we have taken activated carbons, carbon back mesoporous carbons that was taken. So they have a rough surface the through that image. So once that materials have taken and we have collected the ACM image, so you can see these are the materials having rough surface, the surface morphologies that we can see it is rough surface. And later we have prepared some glassy carbons, nanofibers or multiple carbon nanotubes. So if you notice, so this is carbon glassy carbons, this is carbons nanofibers, and this is carbons nanotubes. So these are having a very smooth surface. So that means same materials but different allotropes that you have taken and we have collected that image. So it gives a different type of, means one image or one materials to the another materials. So actual structural changes are there. So in graphites or graphenes we have taken, so here's you can see some layered structures or formations is there in that particular image. Through that we can that specific property of that materials whatever that was synthesized, and based on that it is giving specific applications also that would either enhance or increase, or we can apply depending upon that applications we can choose that materials. So here's carbon materials that was obtained from various biomass source. So we have taken, let's say, cassava starch, glucose, lotus pollens, wheat starch, rami derived carbon fibers, cellulose, deep fructose, corn husk, gelatins. These are the different biomass precursor that was taken to prepare carbon based nanomaterials, and it was collected the image. After that ACM image was collected. So carbon particles, so you can see carbon particles is formed. So here's spherical types. So and glucose derived that carbons was prepared by hydrothermal methods. Here you can see spherical type of droplets or drop type of particles formations is there. And in case see lotus pollens that was taken with nickel oxides, carbon composite microspheres that was forms. So here means, so depending upon the source of materials, here you can see in case of rami derived carbon fibers, so this is carbon fibers, so that was forms. Nano ribbons also is it is forms, so that was derived from cellulose. Okay, so here you can see these flower like structures that is derived, that carbon nanomaterials that was derived from carbon deep fructose materials that was used as a precursors to prepare these carbons. Okay, so depending upon even carbon husk also that was used to prepare nanoporous foamy aerosols that was developed, and gelatins that was used to plate like carbons cryogels that is forms. Okay, so you can see depending different biomass we have used spores of carbons and different type of structures it is forms that material. So once we get image of ACM, so only then we can say that a different type of structures or phase formations is there Based on that, we can say that the materials, what type of materials it has forms and from which source it was taken. So here you can see some metals and metal oxides that can be used as a catalyst also. Here when a calcined materials was taken, so metal oxides that was taken, so the ACM image was like this, and when this metals oxides was reduced and metal was formed, so then that image was taken this. And both metals and metal oxides of this particular, let's say nickels, that was nickel metal and nickel oxides, both was used to prepare multiple carbon nanotubes. So in used samples you can see here both are forming metals nickel oxide metal nickels, hence that was used as a nanomaterials for catalyst developments or for the preparation of the multiple carbon nanotubes. So both the places you can see carbon nanotubes formations is there. So here's diameters may be different. So in case of the nickel oxides when it was used, so smaller diameters CNT formations is there, smaller diameters. And so whence nickel was used as a catalyst and over there CNT was developed, so larger diameters or diameters is larger or bigger diameters formations. Here you can see the dimensions diameters of these nanometers is little bit larger as compared to the calcined material. So if we want to prepare smaller diameter of nanotubes, so then of course we have to go for metal oxides, the nickel oxides we have to use to get smaller diameter carbon nanotubes. And if you want to get larger diameters as compared to the bigger, so then nickel metal. So here's a specific examples, so here's I'm showing. So depending upon our applications, so many ways or varieties of ways are available, methods are available, so we can prepare various dimensions of the nanomaterials. So here just one example I am showing. So some other example also will discuss. The same image was collected and few same image that will discuss. So here's fluorinated tin oxides that was taken, that is the surface over there, titanium was dispersed, and then zinc oxide was coated, and over that CDS was coated. So here initially the titanium that was coated over that FTO glasses, so the nano sheets formations is there. Titanium, here you can see the nano sheets type of formations is there. So here is the same image, with the same image also you can see. And after that when zinc oxide was coated, so here's zinc oxide over titanium it was coated, and the image is corresponding is like this. So that coated also, that was nano rod type of zinc oxide, that is also nano rod type of coated is there. So here also you can see with the help of image we can see clearly. And after that CDS was coated over that surface of that material. So here also you can see it is also that CDS was coated, that was also nano rod type of features or structure was developed over TiO2. Okay, so this is one example. So similarly another was, so zinc oxide nanomaterials that was prepared. So here you can see the morphology or the structure, so that was flower like structure, so that has been formed. So another example, that same materials was prepared by considering other methods. So here you can see it is belt like structures or morphology that has been developed. So depending upon the method of preparations, the same component or materials that would give different type of structures. So here's JDSM5 another example I am showing. So zeolites, that how to prepare that already have discussed. So JDSM pipes that basically consist of silica and alumina, that metals presents at different ratio. So when this particular zeolites was prepared by considering 27, 80 and 150 ratio of silicon alumina by using hydrothermal method. So here you can see when silica alumina ratio was kept 27, the image is like this. The zeolites, the materials that was prepared, it's spherical like of structures. When it was kept silica alumina ratio 80, so then you can see the structures of morphology is rectangular blocks type materials, that formations is there. When it is 50, so its dimension is much more bigger, particles or that type of structure formations is there. So here's this material JDSMs, here's this first three, this was obtained from actually HZ27 acidic, that was 8ZSM, HZSM5, that was treated with NH4Cls. So that was image like this. Hence whence this same zeolites that was obtained from microcrystalline cellulose, that is nomenclature or expressed MZ27. The structures is little bit different. Okay, so means A, C and E, you can see A, C and E. So these three image, so that is made of 8Z27s, 8Z80 and 8Z150. So that different ratio that was used to prepare these materials, and it gives three different type of materials. And bottom three, this and this, MZ27, MZ80, MZ50. So here is also silica alumina ratio is 27, 80, 150 was maintained, and here's that material was started by using microcrystalline cellulose. So from there means source are different. So therefore the structure is also means here is also silica alumina is 27, here is also 27 silica alumina ratio, but structure is different. Here is also 27 was kept, but structural features is different. So depending upon that means elements that we are using to prepare that materials, its ratio is very important. At the same time, the source, sometimes the materials we are preparing in a specific method, the materials we are using, from which source we are using, so depending upon that the structural properties also would change. Next, FECM image of, you can see porous silica that was used, porous silicons. So here we have used, so is porous silicons. Here etching, when we prepared the electrochemicals methods, the porous silicon, so here's one step etching is there. So with strong acids we have to etch that material. So etching times we have varied 10 minutes, 20 and 30 minutes. So you can see with increasing etching times the porosity of that materials gradually increase. So increase and pore size gradually increase. So that is also means etching times is also an one parameter that is very important. So as a result, the materials initially it was less pore to high pore or porous materials we can develop, and with the help of FECM image easily you can distinguish, we can means categorize that it is less porous, it is more porous materials. So that would helps, actually that image will help us to distinguish the way that materials we have prepared, whether it is good or not. So up to what extent the surface area is increased, porosity is increased, that we can easily categorize or distinguish or with the help of image. So here also some TiO2 was used, and here CDS TiO2, that materials was prepared by using some thiolactic acid, that is building block elements that was used to prepare these materials. Its concentrations was varied, means it is different concentrations of these building block materials or thiolactic acid was used when they have prepared these materials or these materials. So by increasing concentrations or different concentrations, you can see 0.1, 0.3, 0.6 molars of these materials or building block or thiolactic acid was used. So by changing concentrations, you can see the structure is also changes, means different concentrations. If you change a particular material concentrations, that would also affect that overall structures or image or morphology of that materials whatever we have prepared. So next is the effect of precursors. I said source material is also important. So here we can prepare iron oxides, that is nanomaterials, that we can prepare by considering different precursor, that is iron sulfates, oxalate, iron chlorides, iron nitrates, or iron D glucose dihydrates, or iron 0 pentacarbonate. These are the source materials that would be gives us irons. So different shapes, nanorods, nanohusk, nanocubes, nanocubes, porous spheres, self-arranged flowers like of structures it would form. So here this materials was prepared, and image was taken. So here you can see, depending upon the source of precursors, the structural property or the materials that would forms different morphology that would gives. Here's also different metal oxides that was prepared by supercritical hydrothermal methods. So here also one particular materials that gives a particular structures. This materials is giving like this. So different metal oxides was taken and its structures also different. Okay, shapes also different and different heating rates. I said so. Whenever we prepared any nanomaterials, so we have to pass through various steps. One of the steps is the calcinations or heatings. So that heating rate is also important. So we can heat at low temperature, high temperature, or heating rates low temperature, low heating rates or high heating rates also we can maintain to once we prepare that material. So depending upon that also the structural property also will change. Means when it was low temperatures heating rates or low heating rates, that materials that would, here you can see stage wise heatings, that is much more better. It would gives the materials having high surface area rather than single step and a sudden heating. So let's say if we want to increase 500 degrees centigrade to 900 degrees centigrade to prepare say materials. So if you go sudden jump, so then there is possibility of agglomerations, annealing possibility is there. If we go step by steps heating, so then there is a chances of means to keep the surface area high and gets better property, high surface area, porosity also, everything we can maintain that materials. That would also affect. So with the help of ACM image we can easily distinguish. Next is the effect of synthesis methods. So conventional combustion synthesis methods, we can prepare nickel irons oxide nanoparticles, and microwave induced solution combustion methods means same materials we have prepared normal convention method, combustion method, and microwave assisted salvo combustion synthesis. So here it has been observed that when conventional methods we are getting 100 to 200 nanometers, that's nanoparticle size, and when it is used microwave assisted combustion methods, relatively smaller nanoparticles we are getting 50 to 100 nanometers. So that is also a method of synthesis that is very important. Calcined temperature is also different. I said at high 800 degrees centigrade if prepared a material, so it would maybe amorphous structures it maintains, and when it is high temperatures, so it would regular sphericals, high temperature it would agglomerates. As a result, some property of these materials will change. After that we can ternary nanocomposite synthesis. Suppose we had using zinc oxide, silver oxides with that copper oxides, three different metal oxides we are using to prepare say specific metal oxide, that is called ternary metal oxides for specific applications. Here we have varied just copper oxides ratio or concentrations 0.01, 0.02, 0.03, 0.04 concentrations, molar concentrations. So you can see by changing that particular metal oxide concentrations, so the structures easily changes. How this to this, here's the morphology of the structure that is changes. So easily with the help of ACM image we can check that. So small particles initially that is forms to crystallines or bigger size particles formations is there. Here is another. So iron smoke that was prepared over reduced graphene oxides. So here's graphene oxides was taken and that was reduced with the help of some gas reductions. So reduced graphene oxide was formed, and then MOF was prepared in hydrothermal method. So autoclave was used and there's reduced graphene oxide was placed, and then benzene dicarboxylic acid or this terephthalic acid was used and iron chlorides, and then iron smoke reduced graphene oxide was prepared. So here you can see, so only iron MOF that was taken, that is octahedral structures that is giving. So here you can see octahedral type of structures when reduced graphene oxides was used as a support materials, over that MOF was developed. So here you can see both are giving structural changes are there in presence of reduced graphene oxides or in absence of reduced graphene oxide when iron MOF was prepared. So Here is also another MOF 5 and nickel MOF that was prepared. Two different structures, means here's nickel was added, here's nickel contamination is not there. So two different type of structures formation is there. Here's iron MOF also, that is, and means modified MOF, iron MOF that was. Here's iron MOF when it was prepared. The structures you can see it is hexagonal spine needles type of structures that is forms. Okay, so when iron MOF was prepared, a specific methods was used that, and after that when amine functionalized, iron MOF was prepared. So its length it is also hexagonal like structure, but the length was elongated after amine functionalizations of these materials. So that is means what kind of structures or morphology changes is there. So the same image would help us to distinguish means the effect of these amines that was with the same materials we have prepared but functionalized with the help of amines and without amines. So two different type of structures formations is there. Similarly others modular also we can use. So different type of structures formations is there. So here's UIO 66 that materials was prepared, and it would MOF type of materials, octahedrons type of structures formations is there. So when TFA was used or acetic acid was used, TFA means difluoro acetic acid was used and only acetic acid is used. So hence only acetic acid this type of structure and trifluoric acetic acid this type of structure. As a result you can see or compare the surface area also. Whence EYO 66 was prepared, its surface area was 908. Whence TFA was used, surface area suddenly jumped, and whence normal acetic acid 1199 meter square per gram surface area was like that. Means depending upon the modulators we are using to synthesize a specific MOF, so depending upon that the surface area also increase. Okay, so depending upon the method of synthesis or different precursors, heating rate, calcinations, many properties, means when we are preparing a particular nanomaterials, depending upon the source, other things, the property also change, and with the help of ACM image, so we can distinguish the changes, the surface, the morphology that is forms when that materials is prepared. So like that way ACM analysis techniques, image analysis, so we of a particular nanomaterials we can analyze that materials whatever we have prepared. Okay, so that it's very helpful methods. Thank you.